Great. Yeah, we can see your screen. So today we have Matteo Romiti from the Austrian Institute of Technology, and we also have Friedhelm Victor. Yeah, and he is in TU Berlin. And maybe you guys can tell a few more things about yourselves if you want at the beginning, just to introduce yourselves, and then you can go ahead with the talk. So the floor is yours.
Okay, I would let Friedhelm introduce himself, and then I will start.
Okay, so yeah, my name is Friedhelm Victor. I'm a PhD candidate at TU Berlin, pretty close to finishing. And I would say I'm mainly focusing on various types of blockchain analyses. So my contribution here in the Lightning protocol is one, but I've mostly been focusing on Ethereum, token networks, and other types of fraud there.
Yeah, I am Matteo Romiti, and I am a research engineer. I'm not a PhD student, and I had the chance to collaborate with all these great researchers, Pedro, Peter, Bernard, and Professor Matteo Maffei. And together we managed to create something that is de-anonymizing the Lightning protocol and the Bitcoin blockchain when putting them together. So this is what we are going to see today. And I think we can just start from our motivation. Mainly, we have this to say at the beginning that Bitcoin and the Lightning Network are thought as privacy-enhancing technologies, and there are many features and fights between breaking the privacy and improving the privacy. So we also know that the Lightning Network is trying to solve scalability issues in Bitcoin. And if it goes well, if they succeed, then the Lightning Network should see mass adoption. Also, we know that there are many studies that are showing us how to attack the privacy and the security, both in the Bitcoin blockchain or also network and on the Lightning Network. But none of them is trying to do this together. So both considering layers together. And another important aspect is that for us, the Lightning Network and the Bitcoin blockchain are communicating in plain text, as we will see. And this is something that it's worth having a look. So what you will see today is listed here. We will start with our research questions, give you a short and brief background for what we will see. We will then dive into the heuristics that we came up with for this work. And they are mainly divided into three parts. One is the linking heuristic, one is the on-chain clustering heuristics, and the last one is off-chain clustering heuristics. Finally, we will show you our results and we will try to validate them. And of course, the takeaways and the future work at the end. So the research questions that we had at the beginning were which privacy and security issues arise from the interaction between the on-chain activity and the off-chain activity. So that's why the title says cross-chain privacy and security problems. Second, to what extent can we improve our view and model of the Bitcoin entity graph and the view that we have on the Lightning topology just by using publicly available data? And the last one is, to what extent can we link Bitcoin addresses to Lightning nodes? And all of these will be answered through this presentation. So the short background here is, for example, starting with the multi-input clustering heuristic, also known as co-spent clustering heuristic. Many of you might know this already, so it's just very short. Basically, here you see two transactions, and the general rule is that if you have one address, at least one address, and in the inputs that is in common between two or more transactions, then you can cluster these addresses together because there is, we suppose, one single entity controlling the private keys of these input addresses. So this is what we think about when we say entity in the Bitcoin blockchain. And in this case, A2 is the address connecting all these three addresses in the inputs. Keep in mind that on the right side, you will usually find the legend. It will change depending on what you see on the left-hand side. And yeah, so this is just the background on the Bitcoin side. And on the Lightning side, we have, to start with, we have two Lightning nodes that we represent with N1 and N2. And as you might know, they announce publicly on the network their IP address and their alias. Aliases are just strings that can be random, can represent some entity, and IP addresses can also be different strings, not IP addresses, but related to Tor, for example. So in the Lightning Network, what you usually do is open a channel, and when you establish a channel among two nodes, you have a channel point that is directly linked to a funding transaction on the Bitcoin blockchain. And this funding transaction can be clearly seen on the Bitcoin blockchain. And with this, we can connect one channel on the Lightning Network with one transaction in the Bitcoin entity graph in this case. And as you might expect, there is an entity that is funding the channel, and this entity might be made of different addresses, and this is the funding entity. And in this case, it's E2, and the funds of the channel are locked in the multisig address that is, in this case, AC1. Now, there is a problem here, and we call it the symmetry problem because we don't know which node is funding the channel. It could be N1, could be N2, but we don't know. We only know that there is E2 that is the funding entity. What happens next is that the channel might be closed at some point in time, and the funds are released from the multisig address, and they are split usually between two entities. And these two entities are, for example, in this case, E2 and E3. And this settlement transaction is can also be seen just by looking at the blockchain. Now, it might also happen that these funds, these settlement funds, these settlement coins can be reused to open another channel. And in this case, this new channel is represented on the between the node N2 and N3. So what we see here is that there is an entity, E2, that is reusing coins from an old channel to open another channel. And at this point, I think we can talk about also the entry and exit points. They are, in our paper, described as just additional entities that are outside the Lightning and Bitcoin interaction. So they are not involved in opening or closing channels, but they are just sending or receiving coins to or from entities that are funding or they are settling channels. So keep this picture in mind, and you will probably see it again in the next minutes. And what we also have to say is that our dataset that is publicly available on GitHub, and you will find the links at the end of the presentation. Our dataset was obtained by running the describe graph command from the LND client. And we collected data from May 2019 till September 2020. And here you can see some numbers. So we collected almost 100,000 public channels, and 38% of them were still open in September 2020. And of course, these channels are linking public nodes. And also you can directly jump into the funding transactions. And from them, you can gather also information about the funding entities, the settlement transactions, and the settlement entities. So we then built the graph that you will see later. Anytime, if you want, you can interrupt, but I will now jump into the core of the presentation, which is talking about linking heuristics. And we will have two linking heuristics, and this is the first one, which we call coin reuse. And as we saw a few minutes ago, we have an entity that is issue that is reusing the coins received from a settlement and then using them to fund another channel. Now, you might have already understood that this entity issue can be somehow linked to N2. There are, for this case, more requirements that you have to consider, and details can be found in the paper. But you can say that the entity that is receiving settlement coins from a channel, in this case C1, and using them to fund another channel, in this case C2, is linked to the node that is appearing in both C1 and C2. So in this case, we can link E2 to N2, the node appearing in both channels. Now, it might also be obvious that if you can assign E2 to N2, then the other entity that is receiving the settlement coins, in this case E3, then E3 must be somehow linked to the other party in the channel. So E3 should be somehow linked to N1. So this is a corollary that we used to improve the linking heuristics. And yes, we can say that E3 can be linked to N1, being both nodes, the node and the entity on the other side of the channel. The second linking heuristic that we came up with is what we call entity reuse. And it is somehow related to the previous linking heuristic, but it's not the same. You need further assumptions to make it the same, and you can find more details in the paper. But the way it works is represented here. So you have, on the Bitcoin side, you have an entity that is funding 3 different channels. They might happen different in time. They might be one after the other, or all of them at the same time. Doesn't matter. What you can then see is that there is one node in common among these 3 channels. And in this case, it is N1. And again, more details in the paper, but the linking heuristic number 2, that is the entity reuse, allows us to link the entity funding at least 2 channels with the node that is appearing in at least 2 of these channels. Now, these were our initial results. So just by connecting nodes to addresses, this is what we got. So we mainly have 19% of Bitcoin addresses in our dataset. So addresses that are interacting with the Lightning Network. They are linked to almost 23% of the nodes in our dataset. Now, one thing to specify is that the entity reuse is actually the coin reuse is completely contained in the entity reuse results. So the entity reuse is more powerful than the first one. Now, how can we improve this? Is this all we can do? There is something we can do, and what we came up with to improve this is on-chain clustering heuristics. And to make it more clear or more interactive, we prepared this plot. And here you can see some patterns. And now I will, for example, show you one. I will focus on something that it's clear to see. For example, here, I'm going to explain. So you see that this is a Bitcoin address, and you see the string. And this address is funding a channel. So this is the channel funding. And this channel is represented by this red node as well. So this channel is between one node called 002 and so on, and another node called hub 19. You also find the node IDs, so 026 and so on, and 03B are the node IDs of these two channels. And what you see then is that this sort of snake, we call it, continues until, I don't know, in this case, 4 or 5 steps. And this is one first pattern that we saw. Another pattern that we saw is this one. And you have basically one entity here at the center that is opening many channels. And so these are at least 2 patterns that you see just by plotting some of the data that we got. Now, this was just to give you an idea. And we can jump back to the presentation to be more precise with the patterns that we saw. So the first one that we introduced in our study is what we call the star pattern. And you can see it in this way. We have one source entity that is outside the Lightning Network, so it's not involved with any Lightning channel. And this entity is sending coins to 3 nodes that are funding afterwards channels. So green are funding entities. And this star pattern happens 52 times in our dataset. It's not a lot. Next, we have the snake pattern. And as you saw before, it is simply a chain of funding entities opening channels. And this pattern happens quite some time. It is happening more than 5,000 times in our dataset. And so this is, let's say, on the funding side. And then we found 2 more patterns that are on the settlement side. So the first one that we introduced is the collector pattern. And as the name says, there is one entity, the destination entity, that is receiving and collecting coins from settlement entities. And these coins are coming from different channels. The last one is quite similar. There is just one intermediate step to collect the coins, and it's what we call the proxy pattern. And as you can see here, we have the same structure. So you have a collection at not at this point, not at the destination entity, but already at the settlement entity. Now, to summarize, this is what we found just by looking at the opening, so the funding transactions and the settlement transactions. So this is what we saw. And as you might expect, there are further details in the paper, but as you might already expect, these 3, for example, E2, E3, E4, are somehow linked together thanks to the fact that they received coins from one single entity. And also, for example, in the snake pattern, you see that there is one pattern that is one structure that is connecting all these entities. So E1, E2, E3 are somehow connected. Also due to the way that when you fund a channel, you usually get back the change, and then you can reuse the change to open another channel. So this is what we found, and it's what we have before the on-chain clustering heuristic. And in the next slide here, you can see that there is this is what you get when you cluster entities, funding, and settling channels. So this is what we refer to when we think about on-chain clustering, specifically in our work, thanks to the fact that these entities interacted with the Lightning Network. So only interacting with the Lightning Network is allowing us to cluster these entities. Now, this was what we did on the Bitcoin blockchain side, but there is also something that we can do on the off-chain, so on the Lightning side. And for this, Freedom is going to help us understanding.
Right, so I'll take over from here. So if any of you have played around with a Lightning client before and maybe tried to open some channels, I'm sure you've come across the service LNBig, which for a long time allowed users to have free inbound channels. And if you look on their website, then you can see that they actually have a bunch of nodes that they seem to be running. And we actually also checked with them if one additional node, LNBig billing, that they don't list there, also belongs to them. But essentially, this means LNBig is controlling at least 26 nodes, and likely there are many other users that also run multiple nodes. And so it's interesting to be able to cluster these and say, well, that's essentially the same user. And the way we did this, we can take a look at the next slide. For each node that we see, we can have an IP address, which we can further resolve to an autonomous system number. So meaning where is this hosted? This could be some Blue Ocean or Host Europe or Amazon service even. And then we have, for most nodes, also an alias. And so the idea is if an alias is very similar, like in this example, LNBig billing and LNBig LND31 that they have, then maybe this is already a good indicator that they belong together. And so in order to do so, we impose the requirement saying if the name is quite similar, then they must, in addition, also be hosted on the same service. They don't need to have the exact same IP, but the autonomous system number should be the same. And so that's the alias-based clustering. And what you can, of course, also do is if you see a node hosted on the exact same IP address, then it's also very likely that the two nodes are controlled by the same entity. And we've visualized this on the next slide, where we would say, okay, LNBig belongs together, and this foo node and bar node, they also belong together. Now, of course, now we need to kind of find out which string comparison measure is a good idea to use. And so there are many to pick from. You could choose, for example, a longest common substring. Many of you may have heard about Levenstein distance, Hamming distances, and so on. We've tried quite a number of them, but what you also have to choose is a threshold. So at which point would you say, okay, they are sufficiently similar so that we would cluster them? And on the right-hand side, you can see a dendrogram visualizing this with a horizontal line indicating a threshold, where we would say, okay, at this particular threshold, then most of LNBig's nodes would be clustered together, apart from the two ones that are marked in red, and some other random nodes that contain, for example, the words lightning, which probably a lot of users would use in their names, is also combined. This is why we impose the restriction saying it must be on the same autonomous system, because for these other nodes to be accidentally in the same hosting environment is kind of reducing the chances of false positives. Now, moving on, we evaluated all of these string distance measures with the requirement that we said, well, the ground truth that we have is LNBig with 26 nodes, so it must find these nodes in one single cluster. And then in addition, we try to maximize the number of nodes that are being clustered. And it turns out that the relative longest common substring, which means it's taking into account how long is the substring relative to the longer string, gave us the best results. And in this case, we were able to cluster about 350, 360 nodes into 126 clusters. Now, if we include the second heuristic that assumes if two nodes use the exact same IP, if we combine these two heuristics, then we end up with 1,100 clustered Lightning nodes into about 300 clusters. Now you may be wondering, okay, what if people use Amazon here? That could lead to false positives. And interestingly, we also found clusters within these 300 that are completely hosted on Amazon, but they're distinguished because their naming similarities are just different enough. So in that sense, we believe the false positives shouldn't be that high, but of course we can't give an exact number. Now, moving on, we can combine the linking heuristics with on and off-chain clustering. So what Matteo showed you before, of course, we can now say a certain node is actually within, is an entity that we can use instead. So this allows us to combine these heuristics, perform the linking afterwards, and then have better results in terms of how many nodes we can actually link. We get to the numbers 46% of all the Lightning nodes linked to 30% of the Bitcoin addresses in our data set. And the interesting part is, of course, that this means now we have also linked IP addresses to Bitcoin addresses, which, from a privacy perspective is kind of a problem. For law enforcement is probably very interesting. Right, and I'll hand back over to Matteo for the validation.
So as you noticed, we talked about different heuristics. And of course, when you have heuristics, you run into troubles if you do not try to validate it. And so this was our attempt to validate our results and our links, our linking heuristics and clustering as well. And this process is a process that can be performed by any attacker. And it is also affecting and interacting with the Lightning Network. So we thought about doing it, but trying to find a trade-off between our validation needs and also not impacting too much on the network. So we didn't go full scale on this. So to do this, you need two nodes that you control, and one is called the sending node, and the other one is called the receiving node, one on the left and one on the right. And what you do is you need to find a node and to link this node to a Bitcoin entity. So we call this node the target node, so the node that you want to link to a Bitcoin entity. So this target node in the middle, you open a channel to this node from your sending node. And of course, this has the cost of one on-chain funding, one transaction. And you open, now I say 100, it's just whatever the unit you want, milli Bitcoin or Satoshi. There is a minimum threshold to satisfy, so you cannot go to just 100 Satoshi, it must be higher than that. But you start with opening a channel to the target node, and then you connect your other receiving node to the Lightning Network, and you make sure that you have enough inbound liquidity. So in this case, I put 50-50, could also be 70 on the Lightning side, and on your side, 30. So you just need inbound liquidity. And there are services providing this. So next, what you do is you need to send a payment from the sending node to the receiving node through the target node. So in this case, we just send 30 coins, and the balances then change accordingly. So on the sending node, we go down to 70, and the target node receives 30. And then the target node forwards these 30 coins to the Lightning Network, and so on, until these 30 coins get to our receiving node. Now, the only cost that we have in this is are the routing fees. There is no additional cost on this because the money we sent from the sending node is received back on the receiving node. And what you do at this point is you close the channel to the target node, and the target node is happy because it received 30 coins. And we are also happy because now we can just wait. And by the way, when we close the channel, we have one on-chain transaction fee to pay. So I was saying we're happy because now we just wait, and the node, the target node, sooner or later will move these coins, and we can see which settlement entity received these coins, and also the way that these coins are then reused in the Bitcoin blockchain. And also, of course, on the Lightning Network, if this target node opens further channels. So this is where we can link, or hope that we can link the target node to some Bitcoin entities. As I said, we needed to find a trade-off between interacting with the Lightning Network and validate our results. So we managed to close, which means first open and then close a channel with 73 nodes. We also managed to send correctly coins to 52 nodes, and also 3 nodes open channel to us. And we also managed to send actually the number of nodes that managed to receive our coins but did not spend them were 31, which means only 11 nodes managed to receive and then also spend our coins. So out of these 11 nodes, we managed to validate 9 of them. And to validate 9 of them means that these 9 nodes were correctly linked to Bitcoin entities with our linking heuristics. So what we obtained from the linking heuristics and the clustering heuristics is the same as what we obtained with this validation process. Again, check the details in the paper because here I'm just giving a rough idea of what we got. And this next part is talking about security and privacy. And for this, I hand back to Frieden.
All right, so of course, now that we've shown you the heuristics on linking and clustering, we can ask what are the implications of this? And so one of the things we can ask is how does the wealth distribution actually look like? Who controls how much capacity? Is there potential impact? What is the potential impact of attacks performed by one of these powerful entities? Can a DOS attack that is very targeted have a large impact? And finally, if an entity controls multiple nodes on payment paths, what can they learn about the payments? And so the first part that we're going to look at is of course the wealth distribution on the next slide. And since if we know that a channel has been created by a certain user because we linked it to a node, then we can attribute the full capacity of this channel to that node. And for all other channels, we assume that each user on each end controls half of the capacity. And if we do that, then it turns out that L big, which I've previously mentioned, controls almost a quarter of the entire capacity of the Lightning Network. And it might, in practice, actually be even more, considering that they open free channels or have opened free channels to a lot of users. But this is kind of an estimate here. The next most capacity shared is not as large, but it's still quite significant. And overall, 80% of the whole capacity is controlled by 10% of the nodes. This kind of relationship, I guess, is not too untypical in financial markets, but nevertheless, it's maybe not what you're expecting. On the next slide, we can take a look at grieving attacks. Now, that's not something that we invented or discovered, but we can check if they are prevalent. And so the requirement for a grieving attack is that attacker has a path of this particular form where he controls the first node and the last node of the path. So essentially, this means sending money to himself. Although the other users don't know this because they don't know that he controls multiple nodes. And then the attacker tries to exhaust the capacities along this path so that the intermediaries are essentially locking up their funds and don't have as much capacity left anymore. And then he just doesn't accept the payment in the end, which means they're all locked up now, the intermediaries, and they have to wait for a timeout, which can be up to the order of several days. And so again, ln big is the node that could have the largest impact if they were to run such an attack, because essentially they could lock up 40% of all channels if they wanted to do this, and something like 22% of the total capacity. The other next largest by capacity nodes don't get quite close to these numbers, but nevertheless could also have quite some impact. Now, moving on to denial of service attacks. It has been reported before in March 2018, for example, that the Lightning Network was hit by a DOS attack, taking 20% of the nodes offline. So this is not just a theoretical thing, but it actually happened before. But the idea now is, what if such a DOS attack would actually target just one of the big entities? So for example, targeting ln big, maybe trying to get a certain hosting provider down. I'm sure that's not easy with Amazon, but for the smaller ones, maybe it's possible. And so in order to get an idea of the impact of that, we simulated this by generating 1,000 random node pairs so that we have payment paths. And then we computed the payment success, whether they could still send money to each other, and the max flow, meaning how much money could they actually get to one another. Possibly through multiple paths, doesn't need to be one, but how much money could they send there? And finally, what is does the network get partitioned by such an attack? So what is the size of the largest component in graph terms when such an attack is performed? And so we're assuming the attack is performed on these high capacity share nodes. And if they did this with ln big successfully, then that would mean the max flow is impeded by almost 35%. Payment success would be down by 12%, and the largest component shrinks by about 5%. Now, it would, of course, be possible for a sophisticated DOS attacker to try and take down the largest entities by capacity share, and then their impact could be even greater if you kind of go to the right-hand side here. Now, for the last analysis on the next slide, we'll look at value privacy and relationship anonymity. So if an entity is on a payment path, then of course they can observe the transferred value. And so it's interesting to see, okay, how many of these payment values can certain entities actually observe? And possibly even more interesting, if an entity is the immediate successor of the sender and the immediate predecessor of a receiver, then they can also know who paid to whom. And so we evaluated this again, this time on all possible paths in the network. But of course, we need to choose a path from one node to another, and we always pick the cheapest path based on a certain Satoshi amount that is trying to be sent. And so the results are essentially that, again, Alan Big has the largest knowledge here, the knowledge gain, I would say, in the sense that they can learn about 40% of all payments value if the payment is significantly large. So for small payments, they only get to something like 5 or 10%, but for large payments, they can see them pretty often. And they can learn who pays to whom for up to something like 15-17% of the node pairs. If multiple of the top entities were to collude and combine their knowledge, then of course these numbers would go up even further, although kind of relationship anonymity cannot be attacked as quickly as just the value privacy for obvious reasons. In the paper itself, we've also looked at wormhole attacks, but we refer you to our paper if you want to find out more about this. So the takeaways are, we've presented 2 heuristics to you on how to link Bitcoin addresses to Lightning nodes. And this means in our best result, we've been able to link a bit more than 70,000 addresses to almost 11,000 nodes. We've presented 4 on-chain clustering heuristics, where we're able to combine 25,000, almost 26,000 entities into 8,000 components. And I've shown you 2 off-chain clustering heuristics that let us combine 1,200 nodes into about 300 clusters. And our validation shows that for 9 out of 11 nodes, we've been able to validate that these heuristics seem to work fine. Now, in general terms, it seems that there are very few influential Lightning users, and in theory, these could be attacked, which might have quite some impact. Or they could band together to spy on users, and one countermeasure as a regular user might be to use alternative paths that avoid them. But of course, that would mean these paths would be more costly. Finally, we want to add that we have about 16 months of data, so from May 2019 until September 2020, which we've made available alongside with our code. So you're free to take a look at this, maybe explore it, maybe have some additional ideas. And as for future work, we think such analysis could also be performed on other layer 2 protocols. So think, for example, about the Raiden network on Ethereum. It might also be possible to analyze private Lightning channels. And finally, in the past couple of months, some new wallet features have been proposed, and these might reduce the effectiveness of some of our linking heuristics. And of course, that could be studied as well. And with that, I close with the resources, links to these resources, and I thank you very much for the attention, and we're happy to answer any questions you have.
Well, thank you very much for the talk, Friedhelm and Matteo. So let me maybe ask the first question here, and my specialty is not around channels, so maybe this is a well-known result, but I was wondering if there is a maybe provably anonymous solution for replacing Lightning on Bitcoin, or if that's not possible.
So the possible answer I can give to the best of my knowledge is that you might use these latest features that are, for example, the partially signed Bitcoin transaction, and that is already allowing you to obtain privacy from the Lightning Network, so you do not, our linking heuristics might fail. On this, this is an answer I can give you now. I don't know if Frieden wants to add something. Also, if Pedro wants to jump in.
Mm-hmm.
Yeah.
Right.
So from my end, I don't know if there is really a more privacy preserving alternative ready at this point.
Right. So I think here we need to consider two aspects. So one is the creation of the channel itself that goes onto the Bitcoin ledger, and there it could be alternatives where you create the channel in a way like in Zcash or Monero, or basically that the creation itself is more hidden than the current Bitcoin transaction. And but at the Lightning Network layer, at the layer 2, there is an inherent problem for privacy that if it's this multi-hop payment, this forwarding of payments. And in a high level, the point is that if Alice wants to pay Carol through Bob, inherently Alice needs to tell Bob how much money needs to be forwarded and by what time in order to be able to recover if some problem happens. So we have been working on privacy solutions for hiding certain cryptographic information like the hash value. So the current Lightning Network uses a hash value to coordinate the payment through the path, and we have been using techniques to hide this hash value and using more like what we call a point-to-time block contract, where instead of using hashes, we use a D-lock point or an elliptic curve point that gets randomized through the path. So it's not the same hash value over the path, but still the values like the payment value that gets forwarded through the path and the time that we need to recover the payment to refund, these are sent in the clear, and they're fundamentally challenging to hide, because as I said, like as an intermediary, I always want to know how much money I'm getting so that I can forward it, and how much time I can give to my next node to recover, depending on what my previous node has asked me for.
Thank you very much. So are there any other questions from the audience?
Yes, I'd like to ask whether a future version of Lightning where we use PTLCs instead of HTLCs will thwart these attacks against privacy that are presented in this paper.
Pedro, do you want to? I am not able currently to answer this question. I don't know if Pedro wants to give his view also, Freedom. I'm not. Yeah.
Yeah, so I think the PTLCs actually will help to hide or to improve the privacy at the Lightning Network layer itself. But it will not solve the issues that Matteo and Freedom showed in this paper, because here it's really the interaction between the Bitcoin layer and the Lightning Network layer itself. To be more concrete, I think the problem that they have found out is that now we can, looking at the Bitcoin blockchain, we can pinpoint which is the transaction that opens a channel, and we can link it to the channel in the Lightning Network, like a single channel in the Lightning Network that has been opened with the corresponding transaction. So we can link these two informations together. And this doesn't have to do anything about how the corresponding channel is used later for a multi-hop payment. So in a sense, there are two orthogonal problems. I don't know if that answers your question.
Yes, thank you.
Right.
Okay. Any other questions from the audience?
I have a couple of questions, if I may. Maybe one thing that I didn't fully understand was, if you could clarify, that'd be great. When you were talking about validation, I didn't quite get, why did you need to send your own payments to validate? Like, what exactly do you mean by validation, and why do you need to send your own payments and establish your own channels?
Yeah. So our goal is to link one Lightning node, in this case, target node in the middle, to a Bitcoin entity. So this was the beginning, let's say, our goal of the paper, and also the goal of this validation. So we want to link the target node with the Bitcoin entity. And the way you do this, at least in this method, is to check how this node moves or spends coins. Now, we can do this if we interact with this node. Because if we interact with this node by opening a channel, we know that we are on the other side of the channel. So we know that if there is a settlement transaction, you have, in this case, so if we close a channel here with this balance, so 70 or 30, so if we close this channel, we know that we are one entity receiving the settlement, so 70 coins coming to us, but we also know that the other entity receiving the coins, the 30 coins, is related to the target node. So with this method...
May I rephrase a little bit, like, am I understanding correct that if you didn't establish your own connection and this node just closed some other channels that it had previously, you wouldn't be sure which of the two settlements goes to your target node or to the counterparty? But here you know that you are the counterparty, so the other one must be... Yeah, okay, got it.
Yeah, exactly. That's the point. And to do this, you need to find a way to do it in a cheap way. And if by using two nodes, you can do it quite cheaply. Otherwise, you could just send the money and just thinking, oh, okay, I just give this money away, 3 coins, and who cares? And yeah, in case you can get it back.
Yeah, I have another question, if I may. When you're talking about if the adversary controls the first and the last node in the path, then the adversary can de-anonymize the sender and the receiver. But as far as I understand, due to onion routing, the intermediary nodes, they don't even know whether they are the first or the last. So how do you get around this? I think it was more towards the end where you had like...
exactly. I'm getting it.
The previous one.
So you're saying, yeah, Pedro, you wanna?
Yes. So basically, I mean, what Freedom says and what we claim in the paper is that if the attacker controls this N2 and N-K-1, then the attacker can break relationship anonymity. This is a privacy notion that assumes a setting where there are 2 senders that are fixed in the experiment, in the game of the privacy. So there are 2 senders and 2 receivers. And the challenge for the attacker is to figure out whether sender 1 is paying to receiver 1 and sender 2 is paying to receiver 2. This is the case on the left, and the case on the right is that sender 1 is paying to receiver 2 and sender 2 is paying to receiver 1. So, and the privacy notion is that if the protocol achieves relationship anonymity, the attacker cannot figure out whether we are on the left world or on the right world. And what we claim in the paper is that this notion is not achieved because it's possible for an attacker that controls these 2 nodes to figure out in which of the 2 cases we are. So that's why we say that we can manage to link sender and receiver in the notion of relationship anonymity.
Got it. Okay. The last question, maybe more high level. Just interested in your view, like to all of the authors. Is Lightning Network kind of destined to be kind of centralized in terms of liquidity and capacity? Like now we have Big and other big nodes controlling a large share of capacity, or if not, what would motivate like regular users or smaller scale users to deposit their Bitcoins and take part in the routing? Because as far as I know now, this isn't happening. Now it's mostly professional nodes.
Yeah,
I would say it's still way too complicated for the average user to really run this easily and have the trust in it to not get their funds somehow locked over some upgrades and so on. But overall, I also think in particular exchanges will find out that the Lightning Network is more and more interesting to them because that way they can allow transfers more easily, which in the end, yes, I totally agree. It seems to be getting more and more centralized, and I'm not sure if it's easy to get around this.
Yeah, my opinion, I think it's not that easy also to make it profitable. So to make it profitable, you really need to have quite a good connection to the network and be always available, and quite some skills to find out which are the fees that you can afford to ask and so on. So maybe we are going in that direction, as we also show with these plots.
Yeah, that's actually an interesting point. So I think about a year ago, or maybe it's even slightly longer, I found a Reddit post by the guy that apparently runs these Big nodes, and he was kind of disclosing how much he's actually making with this based on fees and so on. And it turned out that he wasn't making much at all. I'm sure his server costs are higher than this. And so maybe at the moment, it also really isn't profitable to do this. and that's stopping things.
Yeah, I just want to add that I think the definition of how the Lightning Network works, or how the protocol actually works, doesn't prevent anybody from joining. So it's a public network where you can always join yourself. Whether it's profitable or not, it really depends on exactly how many users use it and how many payments we have and whatnot. And maybe this is only a hypothetical case, but maybe now probably the price of Bitcoin is actually raising, might lead to higher transaction fees on chain, and maybe more people actually will join the Lightning Network. But these are only hypothetical cases, and only time will tell whether users will use it more or not, or it's profitable indeed.
May I add that the previous discussion somehow presumed that having Lightning being profitable is necessarily a good thing. On the flip side, we could say that if Lightning is profitable for some entities, then it gets more centralized in a way. So if the goal is decentralization, maybe that's having Lightning not being profitable, but just being there to avoid Bitcoin fees is good enough for it.
Right. I think this is a really good point, that maybe like somebody with a more economic background will be. I think it's a really interesting topic to look at, and somebody with an economic background should look at it and tell us, this is what is the best trade-off between profitability or not, to get the Lightning Network actually running for a long time. Indeed.
So basically, for having a good system and scalable system in the Bitcoin, so for Bitcoin, a scalable Bitcoin, you need a lot of users that do not care about running not-for-profit activity, basically, and which is on the Lightning Network.
All right.
Well, thank you everyone for the wonderful, very interesting discussion. In the interest of time, maybe we can wrap it up at this point. So I'd like to thank the speakers again for their time today, and I invite you all to join us again next week, where Andrew Miller will give a talk at the same time, which we will announce very soon on the website. So yeah, thanks everyone for coming, and have a great evening. Bye.
Thank you.
Bye,
Thank you.
everybody.